Hi everyone. So I'm going to continue discussing the HSC questions from last year. We'll start with the multiple choice. This is question 5. The diagram below here shows us a solid iron rod, and on the iron rod there are two coils. One of the coils on the left here is actually connected to a switch, and we're told that initially the switch is closed. Okay, what does that mean? It means that it forms a closed circuit. It means that current is forming or current is running. Okay, and so let's indicate the direction of this current. So we've got the plus and minus here, terminals, and so we know that current must be flowing from the positive back towards the negative, and so it's going to flow like so, right? And that is our current. Maybe I'll draw that here. And so we know that when current flows in a circular loop, it's going to create its own magnetic field. And so it's going to create flux that looks like this, right? Where the North Pole is here, and so it's going to create flux like that. Yeah, and eventually it's going to hit this coil. Yeah, we see that this coil on the right here. What's going to happen? Actually, no, sorry. This is the initial configuration. So really, this coil over here is experiencing all this flux, but there's no change. There's no change yet. Okay, the change in flux is 0 right now. Okay, because here is where the change happens. We're told that the switch is going to be opened. What happens when the switch is opened? Well, we know that if the switch is opened, the current isn't going to run anymore. There's going to be no more current. And really, there's going to be no more electricity flowing through that coil on the left here, which means that there's going to be no more magnetic field. All this is just going to go away. Yeah, there's none of this now. Okay? And so this galvanometer over here, or connected to this, so remember a galvanometer is just an ammeter. It measures current. It's going to be measuring the current in this coil. And what's going to happen? There's going to be current. There's going to be induced current in this coil. Why? Well, it's because this coil experiences a change in flux. Isn't that correct? Because initially the switch was open, so the magnetic field looked like this, but then suddenly it all disappeared. And that's a change, isn't it? That's a change in flux. Okay? And so let's have a look at the options over here. Let's start with option A. Option A says it remains at a constant reading, or in other words, the induced current is constant. Well, we know that because there's a change in flux, the induced initially there's no current, and after the switch is opened, there will be current, and so it can't be a constant reading, can it? Part B says it moves from a non-zero reading to a 0 reading. So it tells us that initially it's going to have some current. That's what it means by non-zero reading. There's going to be some current in this coil over here, in this coil. That doesn't make sense because initially the switch is closed, which means that the flux going through this coil over here is constant. The flux is constant. We have constant flux. Okay? There's no change, in other words. If there's no change, that means there's no EMF. Yeah? No EMF. Right? Which means there's no current. No induced current. So in other words, it can't be a non-zero reading in the beginning, and so it can't be B. So let's have a look at C and D, which are admittedly very, very close to, similar to each other. So it moves from a 0 reading. So initially, there's 0 current in this coil over here to our right, which is correct because there's constant flux, which means there's no change in flux, which means there's no induced current. So no current, 0 reading. And then it moves to a non-zero reading, which is correct because as soon as all of this stuff goes away, there is a change in flux. All right, so no more of this, there is a change. Okay, there's a change in flux now. There's a change in flux when the switch opened. But then it tells us it remains at a non-zero reading. Is that true? Because once the switch is opened, there's no more magnetic field. And so there is initially a change, but after a while, there's no more change. There's just constantly nothing. There's just no flux. And so remember, in order for induced current to happen, there needs to be a constantly changing flux. Yeah? EMF or induced current is just this, right? It's the change in flux over time. As soon as this becomes zero, if this is zero, then that means there's no more EMF, right? So it can't remain at a non-zero reading, and so therefore it can't be C, it has to be D. Now we have question 7. A bar magnet, we're told, is moved away from a stationary coil. Which diagram correctly shows the direction of the induced current in the coil and the resulting magnetic polarity of the coil? So let's just quickly test these options with our right-hand grip rule. Okay, so we notice that here we've got a north pole here, we've got a north pole here, we've got a south pole here, we've got a south pole here. Let me also draw in the north poles for you guys, because we're used to the thumb pointing in the direction of the north pole. So let's test out A. We point our thumb in the direction of the north pole, and the current flows in the direction of our fingers. Cool, nothing wrong there. Let's try out B. We point our thumb in the direction of the north pole, and our fingers, our fingers should be traveling up like this, right? Up the coil like so. Okay, so B is incorrect because that's incorrect. That's an incorrect diagram. Okay, it can't possibly be B. Let's try C. Oh, again, that's impossible. The current should be flowing like this for a north pole to appear here, and so it can't be C. And so let's try A and D. We know that the magnet is moving away in both cases, and the magnet is in the same orientation with the south pole moving away, or the south pole being the closest. If the magnet is moving away, remember, Lenz's law tells us that any induced current, right? The induced current will create a B field, or flux, in other words, to oppose change in flux. Or in other words, to oppose the motion. Yeah? So how do we oppose the motion here? How do we stop the magnet from leaving us? Well, we want to attract it back. We want to create flux, right, to attract the magnet back. And so D is the answer because we have a north pole that attracts the south pole here, right? Question 18. We're told that we have a lamp, which is in this circuit, that's connected to a battery here, okay? And so here, let me draw the terminals, and let me draw the direction of the current. This is the initial setup. We've got this loop of wire here. It's got a lamp connected to it. And, obviously the lamp is on. But then we're told that this loop of wire, which has the lamp, moves through this uniform magnetic field, this region over here. Well, what's going to happen? Well, we know, of course, there's going to be a change in flux, isn't there? The coil or the loop is going to experience a change in flux. And that leads to an EMF, which leads to an induced current, because this is a closed circuit. And so my question is, what is the direction of this induced current? And so let's think about the change of flux that the coil is experiencing when it enters. Okay, so when it enters, it's going to have a lot of flux into the page. So let me just draw this loop. I'm not going to draw the lamp. Okay, when it enters first, let's call this entry. When it enters, it's going to slowly get some magnetic field like this, right? Remember, Lenz's law tells us that it's going to oppose the change. So if it starts to increase flux into the page, it wants to oppose that, so it's going to create flux out of the page. This is the flux that it's going to create. It's going to create flux like this to oppose it. And so if we use our right-hand grip rule, we point our thumb out of the page because that's the flux it's creating, and then our fingers curl in the direction of current. And so we know that the current is going to flow in an anti-clockwise direction. Or in other words, it's going to flow like this. If I draw it on the original coil, it's going to flow like this. And we notice that's in complete opposition of the original current. You see, it's in an opposite direction of the original current. And so if we look down here and we look at the graphs that show it's asking us for the brightness of the lamp as the apparatus moves from P over here to Q. So we know that in the beginning, there's going to be a decrease in current, right? Because this induced current is going to oppose the original current. And so there must be a decrease in brightness. And so let's have a look at A, B, C, and D. Where's the decrease in brightness? And we see that it's here. There's a decrease here, and there's also a decrease here. Yeah. So we know by now that it can't be either A or C. Okay, and hopefully by now, your gut is telling you that it's actually B. Because we notice that there's a spike here, and there's no spike here. There's a spike in B, and there's no spike really in D. Right? Well, technically there is here, but it's not the biggest spike. Okay, there's nothing that happens in between here. We notice that as we move in between, the brightness of the lamp increases again to its original brightness. And that's what it should, because in the middle here, change in flux is 0. Or in other words, flux is constant. Yeah? So it should attempt to reach the original brightness. It shouldn't stay like this in part D. This means that there's a constantly changing flux, right? Change in flux, right? But here, there's no change, okay? Change in flux is 0, which is true, okay? And so therefore, it should be B. And if you're wondering why it spikes in the opposite direction, well, we notice that as it leaves, right, it's going to, originally it had a whole bunch of magnetic field lines going into the page, but now as it leaves, it's decreasing, right? All of these X's are going away. And so what this coil wants to do is it wants to replace or oppose the change, which means to replace the flux lines it lost. And so it's going to create magnetic flux into the page. And so if we point our thumb into the page and curl our fingers, it's going to create current in a clockwise direction, which is in the same direction as the original current, which is why there is a spike in the brightness. Okay, let's continue. So question 24, we're told that we've got a solid iron core with 2 coils around it. Now, hopefully that looks familiar. It's a step-up transformer. And we're told in question 1 to explain how the operation of this transformer up here remains consistent with the law of conservation of energy. And it tells us to include a relevant calculation. So we know that the law of conservation of energy tells us that whatever energy we put into a system must be either greater than or equal to the energy that we get out, right? We can't get more energy out than we put in. Okay, so if I put in 500 watts, right, I can't get out 600 watts. Okay, that violates the principle of the law of conservation of energy. But if I put 500 watts in and I get 200 watts out, like that's okay. You know, there's just a lot of loss of energy. That's fine. So if energy in must be greater than or energy out, that in other words, power in must also be greater than or equal to power out. Right? And so let's calculate our power in and power out for this transformer here. Our power in is just our VP times our IP, or in other words, our voltage in our primary coil and current in our primary coil, which is 500 joules per second, or in other words, 500 watts. Remember, joules per second and watts are the same thing. Maybe not. Let me write brackets. Yeah. And our power out can be calculated the same way. It's just this times this, yeah. And so we get 50 volts times 9 amps, which is 450 watts. And so therefore, all we need to really write here is explain why power in must be greater than or equal to power out, except in words, and then show that power out is equal to 450 watts, which is less than power out, which is equal to 500 watts. Therefore, it's consistent with the law of conservation of energy. And that will give you the 3 marks here. Part B says, explain how 2 modifications to this transformer would improve its efficiency. Well, if we look back up here, we notice that we've got a solid iron core here. Yeah, a solid iron core. In other words, it's not laminated. And so the first really obvious improvement is laminations. And what do laminations do in the core? So laminations in solid iron core, they actually, well, they prevent, or really they just reduce the formation of eddy currents, right? Therefore, this improves the, so this sort of, I wouldn't say improves, it reduces the energy loss. From heat produced by eddy currents. So that's the first improvement. What is the second improvement here? Now, you might look at this diagram and think, well, there's not much really. Maybe better cooling mechanisms? Well, the most interesting thing here is that it tells us that the coils here are made using copper wires of different thickness. Now, why do you think it tells us that? It tells us that here the wires, the wires are thinner, and that here, the wires are thicker. So my question to you now is, are thinner wires better for power efficiency, or are thicker wires better? Now, the answer is that thicker wires are better. Thicker wires win. Why? Well, the resistivity, or the resistance of any conductor, is given by rho, which is just the conductivity of a material that's unique to a material, times the length of the conductor, divided by the cross-sectional area. This is the part that I'm concerned about. Okay, this is cross-sectional area. Thicker wires have a larger cross-sectional area, don't they? And so really, there's less resistance, okay? So my answer here would be use thicker wires, because this reduces resistance, and therefore it increases efficiency. And remember, efficiency just means, less power loss or energy loss, right? If we want to be efficient with our energy, we don't want to be losing it, okay? All right, let's continue to our last question. So question 33 says, a proton over here, which by the way has a charge of +1, and an alpha particle, which by the way is just a helium-2,4 nucleus, which has 2 neutrons. So remember, this has 2 neutrons and 2 protons. So really it has a charge of +2. It's fired into a uniform magnetic field, so we're told this is a magnetic field, with the same speed, okay? So V v. And the trajectories are initially perpendicular to the field. Okay? Explain one similarity and one difference. So let's think about the similarities. Oh, sorry, one difference in their trajectories. Yeah. Okay. So the first similarity, I suppose, is the both charged particles. And what does that mean? It means that, well, you should be thinking, by the way, of this formula. You should be thinking that the angle between the velocity vector and the force vector is perpendicular. There's going to be a force like this, right? And which means it travels in a circular path, like this. Yeah? And so too does the alpha particle. There's going to be a force downwards like this, and it's going to travel like this. How do I find out the direction of the force? All I need to do is use the right-hand palm rule, because these are all positive charges. So I point my thumb in the direction of the proton's, movement, velocity, and then my palm, my fingers point in the direction of the magnetic field, which is into the page, and my palm tells me the force. Okay. And so the force I know is up for the proton and down for the alpha particle. And so really, the similarity is circular trajectory. And you can explain this because the velocity vector is always perpendicular to the force vector. And this is what we call, by the way, this is what we call the Lorentz force. I'm not sure if I'm spelling that right, but I think I am. Okay, what is the difference in their trajectories? Well, we know that this trajectory over here to the right actually isn't the most accurate. We know that this trajectory on the right is going to be actually a lot bigger. It's going to look like something like that, right? I'm not going to keep drawing, but yeah. And so why is that? Well, we think about it. We need to think about the mass. The mass of a proton, we're just going to label as m. The mass of the alpha particle, we're going to say is 4m, because the mass of a neutron is very similar to the mass of a proton. And so really, we've just got 4 protons worth of mass there. And so what's going to happen? Well, we know that QVB, by the way, theta here is just 90, so I'm just going to go QVB. We're going to equate that with centripetal force, right? And so that leads us to, when I isolate R is then equal to mv squared over qvb, which is equal to mv over qb. And so we notice that for the proton is just going to be this, yeah? Because m is m and q is q. Q is just plus 1, right? But for the alpha particle, m is now replaced with 4m, v is the same, q is going to be replaced with 2q, and b is the same. And so suddenly we get 2 of mvqb. Okay, so the radius is double than that of r. Okay, and so that's why the difference is that the alpha particle has a radius of, I should say the trajectory of the alpha particle has a radius of double that of the proton. All right, and that brings us to the end. Well, thank you very much for listening. Hopefully that is helpful. Any questions that you may have, by the way, I would love to answer if you just post them up on the Google Classroom, and Miss Ebrahimi will forward those to me, or she may take the liberty of answering it herself. But anyways, have a good week, and stay safe, guys. Bye-bye.